Hello everybody, Adam Lusek here, and today we're going to be talking about video generation models, a little bit about what they are and how they work, and then also an application of actually fine-tuning and creating custom videos with some open source video generation models. We'll start by providing a high-level overview of how video generation actually works and how artificial intelligence models actually do the task of creating a video, and then we'll show how I took WAN 2.1, a 14 billion parameter text-to-video model, and fine-tuned it on old book illustrations to be able to create some of these cool-looking videos like this. So to start a little bit with how they work, we first need to consider kind of the abstract idea of what a video actually is. Looking at this example from Sora, OpenAI's video generation model, we can see that it is a, video as we know it, a picture that's moving, but that is where we get into the actual details here. If we were to pause this and play it a little bit, we can see that a video is actually just made up of a series of images. These are of course called frames. Now of course a video being frames is obvious and nothing new, and everyone knows that, but this gets us one step closer to actually understanding the task of generating a video. Because in order to generate a video, you must be able to generate these sequences of images. Which means that video generation models actually share a lot of commonalities with image generation models. Things like DALL-E, Stable Diffusion, Midjourney, and all of those existing technologies. Only now, rather than generating just a single image, what it needs to do is generate multiple images that follow some sort of sequential consistency. This consistency is what's called spatiotemporal understanding, or commonly referred to as space-time models. Now, when thinking about space-time models, it's easy to get lost in the physics jargon and think of this as some sort of, Star Trek related futuristic model, but really all that this refers to is being able to have something that understands how something changes along time and within the space of a video. In the case of the Sora example, that is of course understanding how the city remains consistent and how the woman here, the subject in the middle, is moving across the scene and maintaining consistency in her subject and features across the scene. Now, as it turns out, actually being able to instill a model with understanding of space and time is not too difficult. We have already explored different encoder models, or those models that are able to take some sort of input, such as text, video, images, audio, and then convert them into the numerical format that AI models need to actually do the transformations and generations. And it's been proven that transformer architectures, the same underlying architecture that powers the large language model, is effective at actually being able to learn to encode and understand videos, both being able to attend to spatial features as well as temporal features. Now, if you're a little bit newer to understanding the underlying architecture for generating things like images, videos, and audio, you're probably wondering, why are you so caught up in these different models that have this strange understanding of what a video is, rather when the task is actually generating a video? And that is because, as it turns out, image and video generation models aren't just one overarching model. There's actually multiple pieces at play that all work towards the final goal of outputting some sort of content. Looking at the quick example of the architecture of Stable Diffusion XL, one of the prior generations of image generation models, we can see that it's made up of not one, but 1, 2, 3, 4, 5 different machine learning models. They have 2 text encoders, which handle all of the actual language understanding and converting your prompts into the numerical representation that the UNet, or the main generation model, is actually going to use to transform from text into an image. And then these 2 UNets are going to work together to output what are called condition latents, or essentially our image from the text but in numerical format. That is then ran through a variational autoencoder to decode it back into pixel space. So converting our numbers back into pixels and colors and whatnot, creating our final image. So in the case of actually creating a video, we need something very similar to this, but instead of just understanding text and just understanding images, we need to be able to understand what videos are. Which brings us back to our lovely Sora model, where you can see a bit of a visualization of how this actually works, taking in some sort of visual input, such as a video or a sequence of frames, and then having a separate model that encodes it and understands all of the space and time and all of the image understanding within it in a number format that can then be used for actually processing and generating further images or further videos based on the input. And so the cool part about looking at image models and how they relate to video models, as Lillian Wang in the phenomenal Lil Log blog here has pointed out, is that there is the ability to actually adapt image models to video generation because we've already done a lot of research and understanding of how to generate videos. So inserting in the actual space and time understanding along with this existing architecture isn't too difficult to do. The actual process of generating images and also videos is called diffusion. And while I'm not going to go into the specifics of diffusion, I will link back to a prior video that I put out that goes much more in depth into how all of these models actually do the generation step of creating the images, audio, and video. But looking at the updated architectures of some of the modern day open source video generation models, such as the WAN model, which we are going to fine tune shortly, we can see that they tend to follow a little bit of the same architecture that we were just discussing. Having some sort of video enabled encoder model that can do the understanding of your input into actually translating into video elements, and then combining this with a few couple models. Things like clip and UMT5 language encoder models so that your text prompt can be converted into the video, running through the full diffusion process, and then of course having another decoder that can take the numbers being output, which represent each of the images in frames and how they change over time, back into pixel space as an output video. But with a little bit of the context and background out of the way of how some of these models are actually set up and work, let's talk about using them and training them. Now, I was inspired by this post that I saw from the user PoRest on Reddit, who put out this phenomenal step-by-step guide on fine-tuning the WAN 2.1 text-to-video model. This entire Medium blog post is a phenomenal write-up and step-by-step guide on exactly what I am about to demonstrate. So all of the credit goes to this phenomenal community member and their incredibly detailed write-up here. And I'll leave this as a link in the description down below. I certainly recommend checking it out and giving it a like. So with this, we need a bit of a reason why or a candidate dataset to use to actually fine-tune our model. In the write-up example that we'll be walking through here, the specific scenario is a dataset of the recently passed away actor Monica Vitti, an Italian actor who was popular back in the 50s and 60s or so. And they were able to use a data set of pictures of her face and frames from her movies to be able to generate new videos using her image and likeness. And so while this proves that you're able to do an actual face consistency and transfer, I wanted to then see if we could do something about style transfer. In the past, I've shown how this is done with image generation models, fine-tuning Stable Diffusion XL based on a subset of old book illustrations. And so, as I teased at the beginning here, I was curious to see if a similar data set would generalize well towards videos. So to start, the first thing that I needed to do was actually prepare my data set. Now, the cool part about WAN 2.1 and the actual libraries that we're about to use is that you can use a mixed variety of mediums to actually fine-tune it. So you don't even need specifically videos to fine-tune a video model. You can use images as well. This is particularly powerful because it's a lot easier to work with images, and there are a lot of readily available image generation or text-to-image generation datasets out there, similar to the one that I'm about to use, which is my subset of an old book illustrations dataset that has just a bunch of, well, old book illustrations as well as text descriptions. So to prepare our dataset, what we needed to do was download a subset of these images and then also have subsequent text captions, which of course I already had in my dataset here, but now I have them downloaded as JPEGs along with text files of the same name. So for each image, such as image 1 here, I have a corresponding text file that is image1.txt. And you can see here that for each one of these, I then have the text, which is an old book illustration of a gigantic wave towers above a small town and is about to engulf it, which looks like what is going on here. So one of the common techniques that you can use when actually preparing your data set, especially for the parameter efficient method that we're about to do, is doing something called Dream Booth fine tuning. And while this is a little bit more complicated, essentially the core of it is having some sort of repeatable phrase or uncommon token that you include in all of your training text examples that will be used to almost trigger the model to follow your style. In the original Google paper here where they demo this, they used a bracketed V that was appended to all of the prompts, and then when they ran inference on their fine-tuned image model with a bracketed V, it was able to maintain what it learned from a limited subset of photos. So we'll be doing something similar. For each one of my texts, I have prepended an old book illustration of A as the starting text here. So you'll see for every single thing that we've got, there's an old book illustration of, an old book illustration of, an old book illustration of, and having this specific starter will help when we're actually running the fine-tuned model later to more guide it towards exactly what it's been trained on. As such, you also won't need as many training examples as you might think. For this specific example, I have a subset of 150 images. What the actual blog and guide that we're going to be following did was roughly around 120 images. For those of you more familiar with training image models, we're not quite at the point yet here with the current model maturity where we're able to get the incredible results that we are able to with image models on small subsets of things like 10 to 15 picture data sets, but collecting 100 pictures isn't the worst task in the world. So now with our image data set prepared, what we can do is swap over to our code to actually set up our environment and get the training started. As you can see here, I am sitting in a VS Code server that's connected to an NVIDIA A40. This has roughly 48 gigabytes of available VRAM, and you're going to want to have roughly that much to be able to fine-tune the 14 billion parameter version of WAN 2.1. Some of the things that you can do to actually make your life easier is use some sort of rented environment that comes built in with some of the functionality that we're going to need. For my specific use case here and what is recommended in the blog, I'm going to be using RunPod. And while not specifically required, RunPod does make it easy to use some preset templates that are useful for image generation and video generation fine-tuning. More specifically, I'm using one of their A40 instances, and then within the pod template, if you go to change template and search, you can type in this specific line and we can get an updated image of Comfy UI. Comfy, of course, is what we're going to be using to actually test our model generations and run the model to generate the videos as it's being trained. If you're unfamiliar with Comfy UI, it is a phenomenal open source tool here that allows you to work with different diffusion-based models in an easily accessible environment. We'll show what that looks like in a second, but with creating this specific pod, we have Comfy UI downloaded here automatically for us. So if you want to skip a step, that's an easy way to do it. But one of the first steps that we need to do is actually download a whole bunch of models. This does not come pre-installed with all of the individual models that make up the WAN architecture, but the Comfy organization has nicely packaged them up into this Hugging Face repo here, including the vision encoder, the actual diffusion model, the text encoder, and the variational autoencoder. These are all going to be the recommended components of actually putting together the full process for our WAN video model. This allows us to very easily download the recommended models by just using a couple wget functions here with the correct respective links. So firing off all of those will start to download the models. Now this can take a couple seconds because some of these are multiple gigabytes long. So while that all downloads, and at the same time, what we can do is go ahead and download the WAN 2.1 model itself, because this is the model that we are going to be fine-tuning. So pasting in that, we can see that it's going to download a whole lot of individual models here into the WAN 2.1 folder because we specified it to do so. While all of those models are downloading, which can take upwards of 10 plus minutes, just gotta be patient, let's talk a little bit about the repository that we're going to be using to actually run the training. That is going to be the diffusion pipe package from TD Russell here. The diffusion pipe tool is an incredible tool that essentially is going to automate and cover a lot of the actual training and behind the scenes machine learning work for doing the fine tuning here. TD Russell has put a lot of time and energy into making this kind of just work and has a great list of features. So make sure if you do follow this and do use this tool to give it a star here. But we'll be using a lot of the different dataset training scripts and supported model architecture that they have outlined in all of the readmes here below. So while we're still downloading all of these nice large models here, I can just go ahead and create another terminal and clone down diffusion pipe and install all of the requirements. And once all of that has been installed, we can go ahead and move the Hugging Face downloaded version of 1.2.1 into the diffusion pipe models folder here. So running that real quickly, we'll move it. And after all of this time has passed, we've also finally downloaded all of the specific models for Comfy UI. So we can go ahead and make a couple extra folders in case they didn't get made and move in the respective models that we've downloaded here into the models folder of Comfy. With that, we can actually go ahead and launch Comfy UI. So just changing to the folder and running the main script. This will go ahead and build and kick off our GUI. And now we have that running as well. We can open up the proxy for it. And once that loads, we can see Comfy here. Now, this isn't the exact Comfy setup that we're going to be using, but in the meantime, what we can do is go ahead and go to the manager and click on Update Comfy UI, which will kick off a quick update to get to the latest version. So let that run in the background as well as we still set up. In the meantime, what we can do is go into the diffusion pipe folder and create a data folder that has input and output. Now, input is where you are going to then insert all of your image and text caption pairs. So let me go ahead and do that real quick. And a couple transfers later, we now have 150 images and their respective image text captions in our data input folder here. All this time, this has been enough time for our Comfy UI to update. So what we can do is actually just close this server real quick and then start it back up to go ahead and fully complete that update. And with that restarted, you'll see that the interface has likely changed a little bit, and we'll come back to this here in a few minutes after we actually start the training. We first need to actually configure our training run. So if we go to our diffusion pipe folder over here and go to examples and go to WAN video, we can see the TOML file that we need to change if we want. There are a lot of extra hyperparameters here if you want to mess around with these, but what I recommend doing is changing the number of epochs down to 100 because we don't want to keep this running forever. And then also we are going to change checkpoint every n minutes to checkpoint every 20 minutes so that we're continually saving our progress. Another important parameter is how many times we actually want to save our model that we're training each epoch. In this case, an epoch means one full run through the training data. So for 2 epochs, that would mean that it would go through and look at all 150 images and do its training, and then do that once more, and then save the subsequently trained model. So that would save at 2, 4, 6, 8, and so on epochs of training. We can keep it at 2 for now. If you want to get a little granular and do super individual testing, you could change it to 1, or if you're setting this and forgetting it for a while, you might want to change this to something like 5 or 10. But for our use case, having it at 2 should be perfectly fine. So we've saved our checkpointing to every 20 minutes, we've changed the number of epochs, and we're not going to change anything else here. So with that, we're pretty much almost ready to go. What I'm going to do is use tmux to create a new terminal that's going to be saved. This is going to help if you disconnect from your workspace. If you're using something like a cloud accelerated GPU, like I am, you can easily reconnect to it and it won't actually stop your training run at all. So I've started that session real quick. Then we're just going to path over to diffusion pipe and kick it off with this line here. This line just comes from their recommended example, but changing to the WAN video example file. And so hitting enter on this will spin up a couple things and we'll actually start to get our video model training. Then over the course of a few minutes, you can watch Diffusion Pipe do all of the automated setup, which is, of course, incredible to watch. And you can also see as it starts to reserve more and more of our VRAM off of our GPU as all of the models begin to be loaded into memory for training. And so very shortly, we should start to actually see some training steps start to get executed. And after a few more minutes of waiting, we can see the first couple steps here being taken and our model training is underway. We've reserved about 36 gigabytes of our 48 gigabytes off of our GPU and things are going smoothly. Now, a word of caution, this is not a quick process. It is likely that to get good results, you're going to want to train on a data set of this size upwards of 10 to 20 epochs. For the model that I'm about to demonstrate, this took roughly about 8 to 12 hours or so, with having to actually test the individual intermediate models along the way. So as all of this is being trained, what is going to start to happen is in your output folder, you are going to start seeing these timed and dated folders pop up. And these are going to be the specific checkpoints where if you do need to restart your training or cancel it and start it back up, you can do that with these. And then every n epochs, which however many you had determined in your save every configuration here, you will get another folder that says something like epoch 2, epoch 4, epoch 6, and within that you will have a safe tensors adapter as well as a JSON file. Those specific files are going to be your configuration and the adapter model itself. This specific type of training is, of course, going to be LoRa parameter efficient fine-tuning, which means we're essentially training a smaller sub-module that's going to fit on top of the WAN 2.1 model and only training those weights to affect our output along the way. This is why we're able to train a 14 billion parameter model with just 36 gigabytes of VRAM. But once you start getting some adapters output into your output folder, what you want to do is take that adapter config JSON file as well as the safe tensors file, hop up over here to your Comfy UI folder, navigate to models and navigate to LoRa's, which are the low rank adapters that we're training, and paste both of those files into here. And now that we have those, which your first that you'll see is going to be epoch 2 in this case, we can actually start to test them. So let's hop right back over to our Comfy UI and start to set this up real quick. Thankfully, our good pal who wrote the blog has provided a workflow that we can input, which just looks like this nice raw text file. And if you just Command A, Command C, copy the whole thing, hop on over to Comfy, make sure you're connected, of course, and then paste, what it will do is create the nice workflow here. So this is where you can see the actual architecture of the video generation model translated into these comfy UI nodes. We have our clip text encoders, our actual diffusion model, as well as a sampler and a variational autoencoder that's going to take in our inputs and create our final output. We can also see that this is where we will specify the LoRa model that we are piping our main diffusion model through. So right now, what I can do is change it to my trained old book illustration adapter right here. And if I want to, I can mess around with the strength. I'll actually set this to 0.85 here for the time being. Then to actually prompt and test, which you can do this while running and training the model. I actually would encourage you to do that is as these epochs are coming out, pop them in your LoRa's folder and then run a test generation. We can start to prompt it right here. The first thing you might notice is that this negative prompt here is completely in Chinese. But don't be too alarmed. All of this negative prompt is just a whole bunch of stuff that community members have figured out. Helps actually guide our model more towards following our existing prompt. A negative prompt is, of course, going to do kind of the opposite of your original prompt, and it is going to guide the model towards not generating towards what you put into the negative prompt. And our WAN model, which is a Chinese and English trained model, can take in both. So the preferred negative prompt is this string of Chinese here that says stuff like worst quality, compression, things like that. So this will just get a bit of a boost of performance, although it is amusing to see if you are a English speaker like myself, a whole bunch of Chinese that you're pumping into the model. But to test this out, what I am going to put in is an old book illustration of a man sitting on a porch, smoking a pipe while smoke billows out of it and up into the air. Of course, we are going to be inserting our trigger phrase of an old book illustration here at the start. And then a lot of these kind of different parameters you can play around with. Affecting the strength of the LoRa model on the original model is something that can affect the actual output, as well as the number of steps and all of these other things here. But for the most part, all that I would recommend is turning down the strength a little bit to about somewhere between 75 to 90%. And trying it out. You can also change the actual size and length of the video and its aspect ratio. So with that, what we can do is click run, and Comfy UI will now actually start to load all of the models. So the first generation that you do will actually take a little bit longer because it's going to load all of the models here onto the GPU. But then you can follow the progress along as it makes its way through all of these processing steps. After a few minutes of it loading, you can see that we are now at the sampler stage as outlined in green. And if we hop over here back to our VS Code terminal, you can see that we now are starting to begin our generation. So any second now, we will start to see some progress on a video actually being made. There you go. And depending on your resolution and the amount of steps, this video generation step can actually take a few minutes as well. So do be patient. I would recommend maybe lowering the resolution down to something like 480p if you're just going to be running a bunch of tests and generations there. And after just a few minutes of waiting, we can see our output video, which from my prompt of an old book illustration of a man sitting on a porch, smoking a pipe while smoke billows out of it and up into the air, we can see that we have nicely transferred over the style from our old book illustration data set, and we are getting these novel AI generated videos here that are nicely in line. So everything has been successful. As I mentioned, however, as you're training, do continually test and generate with the additional epochs and safe tensor file model adapters here. All you need to do is just click R and refresh all of your nodes, and that will allow you to pick different LoRa's once you actually put them into your Comfy UI models folder here. And then any output that you do actually generate with Comfy UI will, of course, go to an output folder here. And if you're using this same workflow, it'll just be a WebP file. But do be patient and continually test, as this does take many, many hours, but it is worthwhile because if you're able to get nicely trained models like this one that I was able to do, it can be super rewarding and super cool. And with that, that is all you pretty much need to know to get a little bit of context and background of how video generation models actually work and how to start using some of the modern open source ones and training them yourselves with either something like a style transfer like I did, or in the blog post example, which is of course going to be linked down below, and what we followed through in the video today, something like transferring a person or a face. Hope you learned something interesting today. If you liked the video, like the video. If you have any questions, leave them in the comments below. And if you want to support the channel, consider subscribing or joining a membership or leaving a super thanks if you have the means. Thank you and have a great day.